Yo, let's do some sound checks. I sound like I'm in. Wow. Wow, wow, wow. Cool, cool, cool. Tight, tight, or not. Let's see. All right. Bear with me while I figure. I don't know if anybody is in the chat. Let me know if you can hear me. Type in the chat if you can hear me. Let's see. How to test. All right. Right now, I hear no echo. See if we hear a delay echo on YouTube. Right now, I hear no echo. See if we hear a delay echo on YouTube. All right, YouTube checks out on the Twitness. All right, YouTube checks out on the Twitness. Twitness checks out. Now on the Twitchness. Now on the Twitchness. Ah, cool. Now. So we got everybody. Everybody can hear me. Yay. All right. Let us go back and start where we wanted. Is huh. All right. Well, didn't have that set up. Well, let's just add it here. Huh? Oh, just get paused. I don't know why it's paused. Let's see. Paused on which? On the YouTube? All right. Got YouTube problems. What the YouTube? That's not what I wanted. Come on. Am I back? All right. Well, if you can hear me, you can hear me. If you can't, you can't. I think it's all working. That's the main thing I was looking for. What? I don't know what's going on. It's not as slick as I thought it was. All right. Oh, that's not the one. Here's what we're starting with. And they look like they're updating. So nope, that's gonna stay. That's gonna stay. I didn't do Facebook this time. It's Twitch, YouTube, and X. Well, go figure. Yeah, it should only be YouTube, Twitch, and X. I did a message on Facebook, but I don't think it's streaming there. All right. Even though your Pooh Bear is here, I can still hear you. Yeah, this one. Oh yeah. I am invisible. So, all right. Hey, wanted to start off today talking about one of my new favorite channels, Low Level Learning. And they get into all sorts of low level code, mostly in C, also assembly. And one of the things our topic for today is lower level learning, which is, well, how does the code actually operate below assembly? And below assembly, by that I mean the internals of the processor. So it's kind of a borderline between electronics, microprocessor versus code. So, but it is in a way a code. So we'll get into that. First off, we don't need this. All right. And we will bring up our processor. So this is our processor diagram. And it has a number of registers, locations, right? And most of our instructions move data from one place to the other, or take two values and put them through the ALU to add or subtract or things like that, mathematics. And then the assembly instructions actually describe how to do those moves and calculations. And they do that based off of an assembly grid such as this. So in our processor, we got 256 instructions, although a number of them haven't been implemented yet. And but this is the individual assembly instructions, and they're encoded in such a fashion as any kind of data move from the A register, for example, to the R register is actually encoded in their position So LAR is actually instruction in hex is 3, 6. And by default, as you can see, all of these light blue instructions are moves. So I'm able to encode the from and to register in the actual instruction. And when the from and to register are the same down this diagonal, not very useful. So those became the system instructions. No operation, halt, interrupt request, clear, etc. Decrement, increment the stack pointer. So when a processor actually looks at an assembly instruction, it takes this address, in this case 3, 6, and it looks that up inside the sequencer. So we'll step back just a bit. We'll say we're going to start this processor all over, reset, and what will happen is the first few commands will actually do things like clear all the registers out and set up the stack pointer. Before I get too far here, let's get this guy going. So we got a little bit better highlighting of the mouse. So for example, we were going to move from register 3 to register 8, or 6 rather. There it is, the R register. And so to do that, we needed instruction 36. So let's see how best to go about this. The best way to describe this is to get into the sequencer and instruction decode logic. And what this is it would be a single ROM in most processors, but since I'm trying to build mine, it's a combination of a 16-bit and a 32-bit ROM, both of them very small. And that was the point I was trying to make. So when you move data from one register to the other, it's moved across a single bus. So they're all talking on the same line. You can't have them all talking at the same time on the same line. And so individual output enables exist for each register. And the output enable of a register and the read from the bus pin from the registers are all encoded into the sequencer. And so what this does is if we want to move a piece of data, say from register 3 to register 6, we have to first enable register A to talk on the bus and then tell register 6 to read from the bus. And so those individual steps are all contained within the sequencer for the command. So here we are inside the sequencer. These are the 3 ROMs. This is just addresses for interrupts, so it's not particularly important. But this one is the instruction sequence map, and this one is the actual sequencer itself. So at reset, the sequencer starts at 0, and as it steps, it just goes from one location and the next of the ROM. The output, the data from the ROM, is broken out into all these lines, and then through a number of other bits of logic to come back here and output these main control word. And it also interfaces with the clock and to interrupt the clock for the halt instruction or reset the ALU, things like that. So this control word controls which of the registers can write and which of the registers to read. And what else did I want to cover about this? I don't know what to describe. Yes, you get to watch the sausage making. Video sausage. So let's minimize that for a second. Yeah, we're good. Yeah, thought I was going to do that. Whee! All right, back to here. So I guess the best way to do this is by demonstration. If we reset the processor and then go into each of the registers and put something in them because they're 0 by default. So put something in the A register, put something in the B register, the DR register, which is actually both the D and the R register. Everything's 1 byte, so let's see, instruction pointer. You see, that's quite complicated. And that's because it's got to read and write in a certain way. Stack pointer. Throw some stuff on the stack. Kind of annoying the way this interface works. It zooms at the same level all the time. So then you have to reset every time you come into something. 100 and reset. Okay. So we've got some temporary information in the main registers A, B, DR, the stack pointer, and the instruction pointer. And the system has just rebooted. The command sequencer is going to go step by step through these values. They get decoded, and then we do operations on the registers. In this case, we're going to start by clearing them all out. So the first thing we do is clear out the A register, the B register. Don't really bother with the T register because it's temporary anyway. Then we get the R, D, zero out the instruction pointer so that we start at the beginning of our operation, or the beginning of our ROM rather. Then for the stack pointer, we want to load FF because the stack starts at the end of memory. And then after we have those, we are now sequence number 9. And what we have to do is take this address here, 5C04. It's a little hard to see down there, but we're about to move that. First, the 5C into the T register, and then the 04 into the instruction pointer. And copy that. And that essentially is jump to main. So the first 2 bytes in the ROM determine the starting point in the program. Now we are over here at 045C, and we're going to start with the instruction 76. So what exactly is 76? Look at our breakdown here. 7 is the D register, and 6 is the R register. And since it doesn't make much sense to move from the R to the D, this is a special instruction that instead says load these next 2 bytes, the 10 and 0, into the D and the R register. Kind of annoying you don't see 0 moving to 0, right? But in any case, so all this time our sequencer has gone from 0 to F. But right now, actually in the next instruction, we're about to actually load the next step in the sequencer is about to load the next instruction from ROM. And when it does that, we're going to look up that instruction in this instruction register sequence map. And did it change for me? There we go. Took one more clock tick. So now we're looking up instruction. It looks like instruction 10, which, let's see. Oh, what do you know? It is instruction 10. Or rather, it's looking at the value of ROM, and it's showing 10 right now, or 10. So in the sequencer, we've already loaded the instruction. The instruction itself was 76. And I guess we missed that step. We're going to have to catch this on the next one. So let's go ahead and finish this instruction out. Here we're about to load the next instruction. We look back here, that next instruction is 9.6. We haven't loaded it into the register yet. Notice our sequence is at B5. As soon as we load 9.6 into the instruction register, we now are looking at sequence 50. So now 50 has for the 2 bits of or a byte of information. That extra byte of information is used to determine whether or not we're going to use the instruction number from the instruction itself as information, or we're going to do some sort of custom information. So in some of these, we'll move things from one register to another, or read from ROM into the T register, for example, and that's just encoded in the sequencer bytes. Seem to be talking too fast for my breathing. All right. How best to do this? Let's go ahead and restart this with something a little simpler. Let's restart. What is the best way to heal this? To show this, rather. Best way to do it. All right. I guess what I'm trying to explain is that the way the processor operates is on the code within the sequencer, which is referred to as microcode. So this processor is a complex instruction set, microcoded, and the code within this ROM is what determines how we move things around based off of the instruction we give it. So assembly actually lies on top of the hardware. And in some processors, you could actually change the microcode and redefine what the instructions do. Very touchy-feely, not touchy-feely, very touchy thing to try. Hard to say what you'll get away with and what you won't. Some days you think you should probably write stuff more. Some days you just feel like playing. All right. Try to see. So, okay, we're still in. Let's reset that. Oh no, not that. Reset. Then we will. Let's see. Yeah. All right. So we refresh from scratch. We're going to sort of take over this program, if you will. We're going to say our actual start address is 8. Maybe not 8. 0A. Then this instruction we can modify directly. Oh, you just can't see that, can you? Eek. Always hard describing this diagram. So much detail. So we're going to read the first 2 bytes. So we should make that 0. And that's going to lead us to this location. And then let's put in, we got to load some values. So we want to load into A from EEPROM. It would be 3.1 for the instruction for load A from EEPROM. So that's because this is the ROM is address 1 on the bus, RAM is address 2, register A is address 3, and that all is nicely aligned with the instructions. As I mentioned before, the vast majority of the instructions are moves, so I might as well encode the from and to address in the moves themselves, or in the instructions themselves. Let's see. All right. So we're going to start off. We're going to show up here at A. We need 3.1 to load a value into A, and we're going to load 4.4, or maybe 3.3. And then 3.2 to load into B, and we'll make that 4.4. So now we've kind of taken over our program, and then 1.1 is the halt instruction. So here we go. Reset. We'll start single stepping through the sequencer. You'll see it's just at 0, 1, 2, 3, 4, etc. We get to down here, and you'll see we notice you jumped all of a sudden to 24. And that's because the instruction 31 starts at address 24 in the sequencer. And to show all of the sequencer, the best way to show that is over here in our program. This is the actual sequencer instructions. What the values in that ROM need to be in order to set A to 0, B to 0, R, D, etc. And do the individual things like increase the instruction pointer, load the location out of ROM into the instruction address, into the instruction pointer, increment the instruction pointer, load the next byte, etc. And then once we get it all started, we just load and run in rapid succession. And the reason we're doing this is that, again, the moves are the most common, and that starts, as we've seen here, it starts at address 24 in the sequencer, and that is all of the load instructions from a ROM, load into A, B, T, DR, etc. They all are executed from the same set of 4 microcode instructions. And the information, again, I don't know how many times I have to why I feel like I have to repeat it. But the information about the from and the to are, in this case, the from is always ROM and the to is different registers. And that's already part of our instructions, so we don't need to do special instructions for each register. And we do the same thing for each other type of instruction. And then we get down into the math, where there's some special, there we are, there's the LDR instruction, and POE instruction, which loads a register and does some math for us. And each one of these sequences is the same sequence for a number of instructions. But we're running out of space in our sequencer, and I haven't finished all the instructions yet. You're gonna need a bigger microcode. So, and then here's the sequence map. So for any given instruction, you can see where it starts the last 2 bytes or last 2 characters where it starts in the sequencer, and the first 2 bytes are additional information. So, for example, the special instructions, I say special because they're not move instructions, but all the instructions over here that do the math and the logic, they start at, say, 72, but then they have different flags for what registers are being used for the math. Because there's only, math is only capable of being done on A, B, and T and the DR register. The other registers can increment and decrement, but they can't actually have complicated math done on them. So I'll show the math grid again. These are the minus, sum, left shift, decrement, increment, and so on. One second. Annoying. Not be on mute. Sorry about that. All right. So, yeah, it's really a borderline between software and hardware when you talk about what's underneath the assembly instructions. And different architectures handle this differently in different ways. They don't necessarily have a microcode. This is sort of the most common 8-bit architecture that's out there. Let's see what else we can get to. All right. So now we got to 24 in the sequencer, and that is the instruction 31 to load into the A register. And so we increment our instruction pointer to get to the next byte in ROM. Actually, not the instruction pointer. It is the instruction pointer. Increment the instruction pointer, get the next byte, but instead of looking at this and loading it into the instruction register as an instruction, we're going to load it into the A register. There we go. Now we're going to increment to the next instruction and load that into the instruction register. Now that's going to redefine what location we're going to do our sequences from. So here we go. We sequence 12. Oh, that seems weird. That is odd. What happened? Reset. Through all that. Get our start address. Here we are in instruction 3.1. We load the instruction. Increment the instruction pointer. So you can see we're showing 33 here, but we're not showing, and we're showing 33 on the bus. So we've enabled the ROM output. And the next step, we'll read enable on the A register. That reads it in. Then we increment to 3.2. And did I get that? That should be right. 3. Oh. That is not the right instruction. That's the fun of hand coding instructions, isn't it? 32 is load A from EEPROM again. Or no, load A from ROM, the ROM address. That's not what I wanted. I wanted 4.1 to load into B. And I should have known that because the first nibble in an instruction is the destination address, and the second number in the instruction is the source address. So 41, and we did that before we actually loaded it, so we're good. Now we load 41, puts us at sequence counter 24. Same for 31. You give me the instruction pointer at 44. 44 is on the bus. Load 44 into the B register. Then we're going to get to 11. Load sequence 11, which the sequencer then disables the clock. So we now, no matter how much the clock goes, we're no longer loading instructions. And that's the nature of a halt instruction, of course. So let's see. Yeah, bear with me while I work out how I want to describe this, because trying to do this without talking it out, like Peterson says, you're not thinking if you're not speaking. So, which is weird in the sense that he seems to be spend a long time saying nothing before he discusses something. I always presume that he's thinking. I guess he's talking to himself, much like I feel like I am. So, well, I may have to reevaluate this later. Yeah, I might come back to this. But for now, let us prepare for and describe the second subject that I was looking to cover today. The number one mistake new programmers make. And you can kind of glean from the image that that mistake might be control copy, control paste instead of printed example code. And so what I'm getting at is it always seemed kind of strange to me that we would teach a programming language not at all like we teach any other language. And what I mean by that is in any other language instruction, you learn to uh, speak first, and then you might learn to read next. But you certainly don't start off writing. So why in computing do we insist on starting by writing code? Really, it should be reading code. And back in my day, what you did for example code wasn't go to a website, highlight, copy, and see if it ran. What you did was you got an example book, you opened it up, and you retyped the entire program. So you are copying from the source, but by doing it by hand, letter by letter, you really begin to see where simple changes have large effects and begin to understand what you're going to have to do most of your career, which is debug. We're not really going to be, or you're not going to really be writing fresh, brand new code for much of your career. And in fact, unfortunately, that seems to be what everyone's preparing programmers for, is a world of block and copy. By reading the code line by line while you retype it, I think you learn to read code properly. So if you, after 2 or 3 examples, if you come across a batch of code that has an error in it while you're typing it, you'll begin to see those things. You'll begin to recognize them. And so I think it just haven't completely formulated how I would describe this, but I kind of refer to it as debug first. Because as you hand type code, you invariably make a mistake, and so you have to, oftentimes it won't compile the first time or the 10th time. So let's see if we do this in a slightly different way. Let's see what this, nope, that's not it. That one. Here's our assembly grid. Look that a bit. Here's our program. Right about there. All right. So when we last left off, I was working on the memory read command. If we go ahead and compile, run. I'm sorry. And we run inside the program. Memory read 1, 2, 3, 4. Boom. And that works quite nicely. But what seems to be messed up is if I do memory read, and let's just do A, B, C. Oh, I don't have a backspace. All right. Memory read A, B, C, D. And 5274 is not A, B, C, D, is it? Now, this did work for the numbers. Let's see. MR1, A, B. Ah, dang it. wrong with my backspace? Anyway. Oh, caused a reboot. We can do that too. Alt. Whatever, we'll just relaunch it. And here in our 1AB CD. And that's because it's too long. 1ABC rather. 5163 is not at all that. So let's debug that. To debug that, we want to stop inside the XTOS function, which is hex to short. Let's see, get to the top. And I think it's failing in this, the is hex digit function. So we can start off. I'll just go ahead and uncomment this breakpoint. And of course, we'll have to rebuild. Build, run program. Oop. MR. Now let's just start off A, B, C, D. There we go. Hit our breakpoint. So POE is one of the special instructions. It loads the address represented by xtos.string and then adds, or rather, it loads the stack pointer into the data register and adds the value of xtos.string, which is 5. And that's where we put it before we called the function. So that's all on the stack. So if we do xtos, we get our data register FFFC. It's located here, and this is the address of the string. So the string is actually located at address 2 in memory, pretty low in RAM. So we're going to load that value into the DR register. Then we're going to get the third character, which here's our character string. And our third character is 41, which is capital A. And now we're going to go into is a hex digit in the B register. So now say, is it a digit? Meaning 0 through 9. Hex digits being A through F. So I think this is where our failure is, but let's go ahead and check. So we're going to jump into is digit. It's going to very quickly decide that it is not between the character before 0 or the character after 9. Tapping a little fast. All right, so it said nope. It loaded a 0 into A and returns. And we're going to check here whether there's an A in 0 or a 1 in A, rather, I should say, by comparing it to a 1 and doing the math. And it wasn't. Let's see. Is it a 0 through 9? It wasn't a 0 through 9. So it jumped over the return, because if it is a 0 through 9, B already contains the value 0 to 9. So we can just return. Otherwise, we're now going to see if it is part of the character set A through F. So we're going to load the value slightly less than capital A, which is the @ , into A, subtract the 2, And let's see, the borrow is set, so it is bigger. So we're going to jump down here, and we're going to load F into A, do the subtraction. And if we had a borrow, it would have been bigger than F, but it's not. Value is the digit, so load 1 into A, load T with 31, which is the difference between the capital letter A and the value of 10, which is 10 in decimal, capital A in hex, which is what we're trying to represent. So we do this subtraction, and something's messed up. So that's our problem. The MBT, or subtract. Here, this is what it actually is. We'll just put it in here and see. This is B minus equal T is what it's supposed to do. It did not do that. First off, it made the destination 0. So, like I was saying before, this might be a problem in the microcode. So the instruction MBT is A8. And in this case, the numbers of the instruction don't line up with the registers because this is a subtraction, not a move. So that is A8. But if we look over here, that's annoying. All right. So we returned. So let's restart and see if we encoded the instruction properly in our assembler first off. So come back over here. Make sure we compile so we're running the latest. And memory read A, B, C, D. Enter breakpoint. Load it up. Is it a hex digit? First, is it a digit? Nope. Now, is it a... This is happening because F10 is compiled in this window and it's single step in this window, and unfortunately it has to jump back and forth, and sometimes I hit it too fast. So let's see. All right, so now our instruction is LTE 31, and then AB is the next instruction, which is listed here as MBT. Well, there's your problem. Minus BT is B minus equals T. This is D minus equal T. I don't even think it did that. But in any case, we seem to be encoding it correctly. I think to fix that would be the assembler. So rather than going through and fixing the assembler right now, nobody wants to see me going through that code. It is not clean. Let's go ahead and just fix this in the way we can fix this. More straightforward, which is to not use that particular instruction. And what we will do A can be 0 after the fact. Let's see. Let's load into A, B from B. Then we can do minus A and T. And that's A minus equal T. That'll do the math for us. And then, but before we return, let's load A with 0. Or rather, load A with 1. The O is for 1, not a 0. All right. So if we change that around, we're no longer using the improperly encoded instruction. Compile. Run again. Run some more. Memory read, ABCD. Hit our breakpoint. Load up our pointer. And we're looking at that pointer. We're going to get the first character. It's 41, which is the capital A. In case you're confused, this is the hexadecimal value of the bytes, and this is the text. So now we're going to go into our problematic function. Sometimes it doesn't come back to this window. All right. So it is not a digit. I'm going to have to change those. I'm going to have to make something else compile. So this ignores, but then I'll be wondering why isn't it working? So, all right. I'm going to compare it to what? We're going to, I could have done it. Should have done this a different way. But anyway, we'll patch it up in a sec. See if it works. No thinking. There. Now that's 41's over there. Now we do the math. We have 10 in A, which is a problem because when we return, we expect 10 to be in B. So let's do this slightly differently yet again. Let's see. We already have our text value in B. So we might as well just load into A and then subtract MBA. So that's E minus equal A. And that should give us the value we're looking for. Yeah. Let's see how that goes. Compile. Run. Run some more. Read A, B, C, D. Load up our location again. All right. We are not 0 through 9. Let's see if we're between at and G. All right. Or at and F, I guess. Oh, come on. All right. Load 31 into A. Oh, whoopsie. Dang it. I hate when that happens. All right. I do not need this instruction. It's already in B. So, yes, better. Compile. Run. Run again. MRABCD. There we are at a breakpoint. Come on. Be nice. Play nice, Windows. The glitch is that every time I update the editor, Ultra Edit, it grabs the focus. Oh, what do you know? Promo stuff. All right. Well, thanks for the info, I guess. Oh. That's how that's done. Well, that was fun. Let's see. That was on the Twitchness. All right. Well, let's see. Where were we? We are going to check if we're a digit. Sorry, I didn't have it where I could see the comments. All right. Get past all this so that there we go. We are not a digit. Oh, come on. Such frustration sometimes. All right. Should really have put the breakpoint closer to the problem. All right. Now, here we are. We have decided that it is something between capital A and capital F. Now let's calculate what it is. It is 10. Then we load 1 into A. Then we return. Then we load 1 into T. Do that math. And since they're equal, we would jump if they weren't. But since it's equal, let's move the value over 4 shifts. That should not have made B go to 0. That should have gone to A0 instead of 0A. That's what the 4 left shifts are supposed to be. What is your deal? Oh, that's right. It didn't return A, did it? It took the difference and it came back with 1 0, which is 16. It is not A. And then when you shifted it, it disappeared. My bit disappeared. So the 31 isn't the difference between the two values. How did that test not fail long ago? All right. Be done with that. So put the breakpoint closer to where we care about it. So in this case, it would be right about here. Just before we set this value, let's put in our Alt No up. Pair. That. Build that. Run that. Run that. Mark. Mark. Episode. 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 Alright. Got to that first break point. Let's just continue. Now we're at this break point. So clearly 31 is not the right value. Where did I think it was? Let's see, for the actual value, play it around in hex here. So 4-1 minus 3-1 is obviously 1-0. So decimal 16, not A. So what we really want to do is subtract from 41 until we get A. And do that the opposite way. 1 minus A is 37. So it should really be 37. Nothing like a bunch of little changes. Build. Run. Sorry. Should really install the foot pedal mute. Jesus. I can mute myself from here though. Argengurk. Some days. MRABCD. First breakpoint. Second breakpoint. 37. Do the math and we get A like we expect. Now we're cooking with math. Thank you. She'd run around with headphones on. All right. So that looks like that's going to work now. So just run. I'm going to do it for every digit. There we go. A, B, C, D. Now we're going good. Get rid of these breakpoints. That one and this one over here, wherever it is. It's easier to find this way. I'll just there we go. F5 RAB1 9. Sure. There it is. And I hope to not need this anymore, but let's just comment it out for now. There we go. Interesting that there's actually something at ABC. Oh, yeah. What did we put there? Let's see if it's just instructions or what. So to find out those kinds of things, we would have to look at what is referred to as a map file. So the map file is generated by the assembler. Always useful when you have a there we go. So this actually shows all of the breakdown of where the instructions are in memory, what line they are related to, etc. Doesn't really tell us everything. Actually, let's see, if this is a symbol that we're writing on, we can find that in the symbol table. There we go. And sure enough, the address that is the start of the dump location that we want to look at is at ABCD. And sure enough, there it is, ABCD. We want to look at what we're looking at. That's odd. All right, so let's see. The command string is at 0. So if we memory read 0, sure enough, here's the command string. Command string length is at 40. 0040. So command string length is 6. Sure enough, that's the length of this command. Let's see, what else we got? 4.1 was the dump ram start, which is it's now 0041. Interesting. It's so overlapping. 4.3 was the dump line. So these are variables that were created as globals back when I didn't have an option not to. So let's see. Because I think most of the RAM is empty. So 1 ABD. Yeah, most of the RAM is empty, so it's not all that interesting. But at least we can successfully convert a hexadecimal address typed in to an address we can use. All right, that's pretty much what I was hoping to accomplish there. The eventual goal for this is to, play some games or do some basic kind of math stuff. This screen allows me to, or this terminal allows me to put characters wherever and move them around. I don't just have to print them out directly. And so in the future, that's what I'm going to do more of, much like the colors and everything you see up here in box characters. Let's see, what else do we want to do? Let's see, let's check around. I think we're just about done with what I was hoping to accomplish, and wasn't exactly what I thought it'd be. But let's go ahead and see what's going on. All right. Doot, doot. My own background music. See how the Twitness is doing. All right. Check on that. All right. Well, that's not really helping much, is it? Let's see. All right. I think that's pretty much what I wanted to cover, and I think I'm probably going to refilm much of it. Anyway, thanks for hanging out with me. If we eventually get some viewers, we might have some Q&A. So, I know. Be more consistent. Show up every day. That's just not how it goes for me lately. All right. Let's see. We got our memory dump function working. Yeah. So one of the. What else do we need to do?